Hi everyone, I'm Ruslan. I'm working on Kotlin and Android infrastructure at Meta. For the past 5 years, I've been working on various parts of mobile infrastructure at Meta, and for the past 2 years, I was focused on making Kotlin and Android builds faster. Today, we are going to talk about our migration journey on new Kotlin compiler frontend. So, one second. Yeah, sorry. In order to understand what K2 is, let's do a brief introduction into Kotlin compiler and what parts does it have. For simplicity, let's focus only on Kotlin compilation for JVM. So compilers typically have backend and frontend. Compilers' frontends are responsible for parsing the source code of program and generating an internal representation, usually called abstract syntax tree or IST. The IST then used by the rest of the compiler to perform various analysis and transformations of the code, such as type checking, optimizations, and code generations. The front end also performs validation of the code. Compilers' backends are responsible for generating machine code or bytecode from the abstract syntax tree. The backend takes IST and generated by the front end and performs various optimizations. K2 is a new Kotlin compiler front end, which was completely rewritten and optimized. So today we're talking about our migration journey, how an optimistic K2 migration can look like. You just need to update your Kotlin compiler version and to pass correct language version flag. Can it be easier? From Kotlin 2.0, K2 is default, so we don't need to specify a language version anymore. What's going on? Yeah. So, but unfortunately, it didn't work in that way for Meta infrastructure. We have enormous amount of code, complex build setup powered by compiler plugins, and custom Android toolchain. So beside the compiler version upgrade, we needed to migrate our code base to make it K2 compatible, and we need to migrate our compiler plugins and our custom build toolchain. We started working on making our infrastructure K2 compatible back in mid-2023. So let's talk about why we started K2 migration at the first place. K2 is new default, so it means that it offers new language features and provides exclusive bug fixes. K2 is faster, and K2 has more consistent behavior, and it's better in exposing bugs. We have recently seen one of the examples in our code base causing the runtime crash in K1. So getting back to the example, in the derived Kotlin class, we are shadowing the field in Java with private field in Kotlin. Shadowing Java fields with invisible Kotlin fields was causing runtime crashes. In Kotlin 2.0, new compilation error was introduced. The compilation error covers the provided example with an error, but only for K2 frontend. Such example make usage of K2 safer. 2 years fast forward, up to 95% of our models were migrated to K2, and it improved our build speed in average for 20%. K2 has introduced a number of changes which made it more consistent, and compilers' behavior is more predictable in comparison with K1. You can read more about these changes on K2 release notes. Let's get to an example. We have a model A defining a simple generic class. Model B with a function consuming a lambda using the previously defined class as a type parameter. Model C, where we run the function from model B. The model C doesn't use types from model A, but it executes a function which has the type item in its signature. How many of you would expect that model C needs to depend both on model A and model B? Please raise your hands. So let's see what happens if we define our dependency chain as following. Model B only depends on model A, and model C only depends on model B. When we compile model C with K1 and K2, we receive different compilation results. The build succeeds with K1 and fails with K2. K2 ensures that lambdas are accessible within the compilation unit. It makes the code more predictable and compiler plugins development more robust and easier. In order to fix the compilation error, we need to pass model A as a dependency on class path for model C as well. So let's talk on what made K2 migration challenging for us. First reason, our Android code base is huge. We have more than 20 million lines of code, of Kotlin code, lots of Java code, and some native code on top of it. We use Bug2, an open source build system, which is language agnostic. And we also have a heavily customized Android build toolchain, highly optimized for quick incremental code iterations. A lot of it is powered by complex compiler plugins infrastructure. So 20 million lines of Kotlin code is a lot of code. Large code bases have complex dependencies and architectures, making it difficult to ensure compatibility and stability during migration. K2 provided increased bugs exposure. K2 enhanced errors and detection capabilities can reveal hidden bugs and inconsistencies in the code that were overlooked in K1. And K2 is also more consistent in language usage. K2 emphasizes consistency, and some parts of code which relied on inconsistencies in K1 may not work with K2 anymore. So let's get to an example. We have a function returning a listenable future with type SUMClosable. SUMClosable is a nullable type. And we are declaring a variable. And we are assigning different values to this variable based on condition. So the declared variable is returned at the end of the execution. So in this example, in function signature, SUMClosable is nullable, but the return type is not. Does it look confusing for you? The code looks confusing for me. It does look confusing for K2, but not for K1. K1 was compiling the code fine. In K2, the type system is more strict and requires that the return type of function match the expected return type exactly. This means that if function is expected to return a nullable type, K2 ensures that it will. On the following example, on line 11, we're using a safe call operator on an integer type. And on line 12, we run setText function, which accepts non-nullable string. I would expect the compiler to give an error on such example, but I wanted to ask someone else, so I asked AI. AI also thinks that compiler should give an error because setText expects non-nullable string, but safe call operator makes the type nullable, so we should have a type mismatch. Probably, as you already expected, K2 gives an error for this case, but K1 doesn't. In order to better understand what has changed in Kotlin compiler frontend for compiler plugins development, let's start with an overview of old frontend architecture. So old compiler frontend has separate entities for syntax tree representation of the code and for semantic info. Source code of Kotlin programs is a plain text. Compiler parses the text according to language grammar into a syntax tree. Syntax tree has expressions, declarations, statements, modifiers, type constructs. You can see syntax tree as a product of parsing a single unit. Each node in the tree corresponds to a language construct. So, old compiler frontend parses the code and creates structure representing the syntax tree. The structure is called PSI. In the example, we construct element of type person. Analyzing PSI, we can know that we have a function call with the identifier person, but we don't know anything about the type person, and that it's actually a constructor call. In K1, they had separate entity for semantic analysis. Semantic analysis result was representing in binding context. K1 compiler frontend was providing binding context where we could get resolved names, type descriptors, while inspecting PSI tree. New Kotlin compiler frontend introduced a new structure called Front-End Intermediate Representation, or FIR. FIR combines both results of parsing, so it's a syntax tree, but also it has results of semantic analysis as well. So, looking on FIR of previous example, now we can know that we have not just only a function call, we have a constructor call, and we know what type exactly is constructed. K2 plugins API is based on FIR extensions. We have 4 main type of extensions, and mostly all of them are used within our compiler plugins infrastructure. We have several critical compiler plugins which are heavily used across our code base. Mainly, we have 2 categories of compiler plugins. First one is build speed optimizations, and the second one is our internal framework. So, why do we do build speed optimizations at the first place? We have a simple build graph. At Meta, we are using open source tool called Bug, powered by remote caching and remote execution. So the build time for a build graph depends on how long does each node in the graph take, but also it depends on how many nodes were chained in the graph, how many of them can be executed in parallel. We have optimization called Kasabi. Kasabi is a set of compiler plugins which performs Kotlin source-only ABI generation. So when we're building a bug rule, bug creates an action for generating source-only ABI jar, which only contains public signatures of the code, and it also runs a library jar generation. So applying Kasabi to the previous example, now bar doesn't depend on library jar of foo and const anymore. It depends on their ABI. ABI nodes, they're lightweight, and they only need to run compiler frontend. So we early terminate after generating ABI in the frontend, and now we can run foo, bar, and const in parallel. So, Kasabi's set of plugins. We have 2 Kotlin C invocations. One is full compilation, where we produce library jar, and another one is source-only ABI generation. At the moment of this talk, we migrated our main compilation on K2, and we run within the main compilation, we run a plugin which is checking if the code base is compatible for source-only ABI. And in the second invocation, it's still on K1. We generate stubs for dependencies, and we also generate ABI for the compiled module. So, as I mentioned, in the main compilation, we run various checks to ensure that the module is can actually be compiled with source-only ABI. One of these checks is checking that all types used in model are explicitly imported. For example, in this example, we have on-click listener, but we don't import it explicitly. So it means that only from the source code of the file, compiler cannot infer what type exactly an on-click listener is. By this reason, we are running a check in a compiler plugin, making sure that all use types are explicitly imported. So, how did we migrate the checker to K2? What capabilities do we need to run this check? First of all, we need to get all imported names in the file. Then we need to visit all the types which are used and to make sure that these types were imported. And then we need to give a compilation error. So the most suitable extension point for this was FIR file checker. FIR file checker is a type of FIR checkers extensions in K2, which are operating on FIR file level. In order to visit referenced files, we are implementing an FIR visitor and reporting errors based on the visitor's results. File type ref visitor is an implementation of FIR visitor where we override visit type ref function and we can handle type refs. In our case, we are checking that the types are part of the import block. Another example of build speed optimizations we have compilation avoidance optimization. So we have a compiler plugin which dumps all the class usages within a file and it dumps it into a file on disk. So it was easy to handle this optimization in K1 because K1 had single analysis handler extension where we could both traverse types and also run some custom actions when the traversement is finished. But K2 doesn't have it. So K2, when we have custom FIR checker extension, K2 runs extensions by itself, and we don't have a point where we can make sure that all the extensions has finished. So in order to implement the mentioned plugin in K2, we had to collect all the types in FIR. We had to define a custom service which was representing state, and we shared the state between front end and back end, and we are dumping this state into a file on back end in an IR extension. Yeah, so we're using FIR to IR extension point to dump all the collected files, all the collected types. For one of our frameworks, we needed to change FIR during compilation. So let's not go deep into what does the framework do, but let's talk about it on a custom example. So we have a mock function which accepts long and mocking context, and we want our users to, we want to have control of the function execution points to provide simplicity for the users. So we generate source code in Kotlin symbol processor, and we insert the references to generated types in FIR transformer. So if we were changing the actual source code, that's how the transformed code would look like. So on line 2, we have inserted new parameter to the constructor, and on the line 4, we changed the function call side, inserting two new type parameters. And we are also using the constructor parameter on the call side. So in order to implement it, we have following problems. We need to transform call side. We need to transform constructors and to add new parameters. And we need to make these parameters accessible within the call sides. Also, we need to make sure that the transformation happens before the compiler's front end gives us an error because we are using non-existing function. So we're using an FIR transformer to change the constructor and call sides. Transformers is an API allowing to change FIR while visiting it in a compiler front-end plugin. So to run the transformations, we are using extension point, which is happening before the FIR checkers. Because FIR checkers, that's the point in the compiler where it will give us an error because of the usage of non-existing function. So the extension point we've chosen is FIR status transformer extension point. So the hardest part that we need to make the constructor parameter accessible for the call sides. When you amend source code, you can just add the parameter and front end will add a property for you. But when we do it in FIR transformer, it doesn't happen. So we need to make it by ourselves. So we are using FIR declaration generation extension where we declare a new property and we replace an initializer for this property, referencing the constructor's parameter. Debugging was also a hard part for this compiler plugin because all the changes, they happen in memory in FIR. So we implemented a custom FIR file checker, which just dumps the FIR files on disk. So we can see what FIR we have as a result of our transformations. And we can run different snapshot testing to make sure that compiler plugins developers introducing their changes, they do it intentionally. So another thing we had to work on is KSP. KSP is symbol processor by Google, and it replaces KPT for most of our cases. One of the existing problems with K2 is the state of K2 and KSP support. KSP2 is a standalone tool supporting K2, and it required for us to adopt it in our build system to make our build support K2. KSP1 used a compiler plugin which could be run together with the main compilation. As a first stage of our K2 migration, we split our Kotlin C invocations into two parts. The first part runs KSP1 as a compiler plugin in K1 Kotlin C invocation, and the second one performs the main compilation with K2. From version 2.0, KSP is standalone tool, so our plan is to replace the first invocation of Kotlin C with KSP compiler plugin with KSP2 standalone invocation. So K2 and Kotlin 2.0 is new default. K2 is faster, so we have about 20% of build speed improvements in average. We had to migrate our compiler plugins, and now we're experimenting with KSP 2. And also K2 adoption improved consistency of language usage in our code base. Thank you.